Welcome back. Still on moments of inertia. So we want to take an example on that will be another example anyways. But now we get to apply the fundamentals we've learned about moment of inertia of a rectangle. Yeah, in this case to solve this particular problem. So this is an example, worked example on evaluating the moment of inertia of an area by direct integration. So let's have an example on direct integration first. So we have the problem written here. So let's me open to that page. So it's problems on moments of inertia. It says this question says determine by direct integration the moment of inertia of the shaded area about the x and y axis. So the axis is at the base of this shape. We have the equation of the shape given to us as y equal to kx squared on this face. Of course, you can see this is just a horizontal line at this end. So we will reproduce this shape first so we know what we're working with. So let's open our notebook and we have this shape to deal with. So just putting the solution here directly, and the shape is like this, and then we have a horizontal line here. So this is horizontal, and then we are told that there is this is a curve with equation of y equals kx squared. So this is the area we want to find its moments of inertia. We want to get its moments of inertia about the x-axis and also about the y-axis. And how do we go about this? Of course, we'll have to make use of, let's check to be sure that we have extracted all the details. Yes. So we're told that the dimension of this is A, that's the length of this horizontal side is A, the length of the vertical side is B. So let's get back to that. So this length is A, that is the distance from this to this point is A, okay, the distance along the horizontal, and we're told that the distance along the vertical is B. So let's see how this works. This distance is B. Okay, just to be doubly sure that we've extracted the details properly, we have y equals kx squared. We have horizontal distance A, vertical distance B. All right, so we want to get the moment of inertia by direct integration about this x-axis and this y-axis. So we're going to make use of the ideas that were developed in the last lesson. So to get a moment of inertia about the y-axis, for instance, we could use a horizontal as a vertical strip, and to get moment of inertia about the x-axis, we could use to get moment of inertia about the y-axis, we could use a vertical strip that is just parallel to the axis. So we can use a strip, a rectangular strip that is parallel to the axis. And if we want to get for the x-axis, we can also use a rectangular strip that is parallel to the x-axis. So we can do that. That is always acceptable. We'll always get, it's guaranteed to always work. So far the shape is simple enough for us to do that, then we are good to go. But in this case, we are going to use a single strip to get both of them. So just follow how this works. And to do that, we'll make use of the results we already obtained, which I said you should memorize, you should know by heart, or you should know offhand or off heart, anyhow you call it, so that you'll be able to make use of that elsewhere when you need to get some the moment of inertia of some other areas. Okay, so for this case, we will reproduce the area, the shape this way, and this is some horizontal line. Then for us to get moment of inertia, let's say about the y-axis first, we can say that we want to use a vertical strip. So let's say that vertical strip, let me not put this here so that it becomes a bit more obvious. So I want to use the vertical strip. I'm going to use the vertical strip, this strip that we're defining now. We're going to use it for both of them, both the moment of inertia about the x-axis and moment of inertia about the y-axis. So first and foremost, when you have a situation like this where you have the equation of some curve on that area given, the first thing you should do is, if the equation involves some constant, evaluate the constant first. That means that a typical problem, any typical problem, any kind of problem in this case anyways, that involves where you have an equation of some curve on the particular area, and the equation involves a constant like what we have here. This k is a constant. How do we know is a constant that needs to be evaluated? If the constant here does not relate with the parameters of the area, we know that we want to get moment of inertia. Moment of inertia should be in terms of the parameters of the area. Just like when we did it for a rectangle, the result was bh cube over 3, hb cube over 3. H and b that appeared in that result were parameters of the rectangle, length and breadth as the case may be. So for this area, these are the parameters of this area, b and a. So our result must be in terms of b and a. So this k, we have to evaluate it also in terms of b and a first before we begin to do anything here. So how do we evaluate this b and how do we evaluate this k which is in this equation? So just understand this statement, or the meaning of this is to say that this particular curve here at this edge is given by or satisfies this equation. So it is defined by this equation. That means that now we know that when we have an entity like this and we have its equation, it simply means that is the relationship between the x coordinate and y coordinate of any point on that curve. I mean, the equation of a curve, or indeed any geometric entity, is simply the relationship between the coordinates of any point that lies on that entity. So if this is the equation of this side, I mean the curve we have here, that means any point on this curve must satisfy this equation. That's the idea. So that's the idea that would help us get the value of this constant. So it's obvious that the constant, this curve passes through the origin. So the origin must satisfy this equation, and that's quite straightforward to see that when x equals to 0, x is equal to 0 at the origin. We substitute x equal to 0 here, y is equal to 0. So that confirms that indeed the curve passes through the origin. Okay. Now we can't use that because if we did that substitution 0 0, it doesn't give us anything. So it doesn't tell us the value of k because we're just going to have 0 equal to 0. But we know that the curve also passes through this point here. The curve also reaches this point, and we can get the coordinates of this point. So when we get the coordinates of this point, we know they must satisfy the equation of this curve. So that's the first thing we do before we go ahead to solve this problem. If not, you will have a result that carries k, and that will be meaningless because we have not specifically done that or evaluated that for this particular area. So let's go ahead and get that first. We know that this curve passes through the points y equal to, it passes through this point up here. So we'll come back to talk about these coordinates. So we say that for the curve y equals kx squared, I said this is the first thing to sort before we begin to do the other calculations. For the curve y equals to kx squared, we see that it passes through this point. So what is the coordinate of this point, or what are the coordinates of this point? So that means we get what is the x coordinate of this point. We trace this down. What is the distance along the x-axis from the origin? That is a, and it is to the positive side. So this is a comma. What is the distance along the y-axis? Okay, from the origin to this point, it is b. So this is a comma b. That means at this point, x is equal to a and y is equal to b. That is the coordinate of this point. So for this curve, we know that the curve passes through the point. This for this curve, we say that when x is equal to a, y is equal to b. That's the meaning of this. Because it passes through this point, it means that on this curve, when x is equal to a, write here y is equal to b. So make use of that information to get our k. So by substituting into this equation of the curve, we'll have y is equal to b is equal to k into x, which is a squared. And from here, we will get k to be equal to b over a squared. So That means from all of this that our y is equal to b over a squared multiplied by x squared. So this is the equation of the curve that we are interested in, that we are going to use here as we proceed with our calculation. Please, this is very essential. It is so that the parameters we will obtain, or the results we obtain, will be in terms of the parameters of the curve, something that we can easily read off from the curve and determine what the moment of inertia will be with respect to the axis of interest. Okay, so we're done with that. So let us get ahead. Let us go ahead to study what this should be now. We know this is our elemental area. So the small width here is along the x-axis. So this is basically going to be the x. And if we want to get this elemental area, the A will be given by, so what is the area of this rectangle? So this is approximated as a rectangle. Yes, we know it is not a rectangle because of the shape of this end, but we'll approximate it as a rectangle. That is the idea with this. So approximating it as a rectangle, we know the width is the x, then what is the height? That is what's the distance from this point, okay, to this point. We know from the details given that this distance along the y-axis is b. Okay, we have it right there in the question statement. And we now want to get this distance from this point to this point. We don't know what it is. But one thing is sure, that if we are able to get the distance up to this point, that is the distance from this point to this point, then we can subtract it from B. When we subtract it from B, to give us the width of, to give us the height of this rectangular strip. So that's what we're going to do. Now, how do we know the this distance here? How do we know this distance from this point to this point? That is why we are given this equation of the curve. So this tells you that on any point, or at any point on this curve, once we know the x coordinate, the y coordinate on that curve, which is the distance we're interested in, that is the distance along this along the y-axis, of course, perpendicular to x, is going to be given by this equation. That is the meaning of this equation. So it relates, for instance, if you get the x coordinate of this point, if we're interested in the x coordinate of this point, that is just going to be the distance perpendicular to the y-axis, okay, which is the x that we are interested in. So if you wanted to get x at this point, that is just this distance. So if we have x at this point, what will be our y here? That y will be given by the equation of the curve. So y will be equal to whatever we have obtained now, which we said is b over a squared multiplied by x squared. So this will be our y at this point. So basically what we need is, we know this area should be, the x is the length, so we keep that. We're going to use it to multiply something. That is this width multiplied by this height, and this height is b from this point to this point minus y. So this is basically going to be b minus y. So whatever y happens to be at that point. Okay, when we subtract it, so if we are here, our y will be bigger, and then our elemental area, if we put an elemental area here instead, will be smaller. But we know that anywhere we are along this, so far we are using this vertical elemental strip, the height of it will be captured by this parameter b minus y. So that's what's important to us. So with that idea, we will now say that, okay, we have the elemental area dA. Okay, we know the distance from the distance perpendicular to the to the y-axis, which is x, and now that means we should be able to get our moment of inertia about the y-axis. And yes, that is true. We will now say that the moment of inertia about the y-axis should be equal to integral of x squared, okay, the a, taking over the entire area. And if we simplify this further, this will be integral of x squared. We already know that x is captured by the elemental area, but the distance of the elemental area, which is perpendicular distance from the y-axis. So we are good to go. There's no modification required for this x squared. Then for dA, we have b minus y multiplied by dx. So this is going to be b minus y multiplied by dx. So we'll come back to y and the meaning of y shortly. So what else do we know about this, or do we observe now? Because our dA on substitution now gives us dx, it means that this integral will be taken with respect to x. So if we are going to integrate over the entire area, we will ask ourselves, how does the x coordinate vary over the entire area? So looking at the entire area of interest, this entire area of interest, so how does x coordinate vary? You can see from this extreme, okay, if we find out what is the x coordinate at this extreme, this is the origin, so x coordinate at this point is 0. What is the x coordinate as the at the other extreme? This is the other extreme, the largest coordinate you can have. So at this point, what will be the x coordinate? That's the distance from this point to this point. It's the same as the distance from this point to this point, okay, which is given in the question as a. So that means x, okay, on the entire area, x varies between 0 and a. So if we will integrate with respect to x over the entire area, our x must go from 0 to a. So that's the idea. So the next thing now is, what is this y here? We know we're integrating with respect to x. We can't see y is not a constant, obviously. So we can see that from our diagram, y varies with the position of the elementary strip, I mean the rectangular strip or elemental area. So y varies with that, and the variation of y with respect to x there has been given by this relationship, which is the equation of this curve. Okay, so it is given by y is equal to b over a squared multiplied by x squared. So we're going to substitute that here. So this will give us integral from 0 to a of x squared into b minus, so what's our y squared now? B over a squared multiplied by x squared. So this is now the x. So now we are good to go. We have x in the whole expression and some constants. We can move out the constants when we get to when we get to simplify them, and we can integrate whatever we have left. So this is now easy to deal with. And so we will work on this integration now. Let's firstly expand what we have inside here. So this is going to be integral from 0 to a of x squared times this. So we can have that as bx squared. And then x squared times this, that is plus b over a squared multiplied by x to the power 4. And then we take the integral of all of these with respect to x. So this will be equal to integral from 0 to a of, so this is going to be integral of bx squared. So we can integrate each of these now. Let's just integrate them directly. We know these are constants. B is a constant, b over a squared will be a constant as well. B is a constant, a is a constant. So b is a constant, and b over a squared is a constant, so it's straightforward to integrate this. We're going to have this to be b, okay, then integral of x squared with respect to x, that's x to the power 3 over 3, plus b over a squared is a constant, so we can leave that out. Then integral of x to the power 4 with respect to x, that is x to the power 4 plus 1, that is 5 divided by 5. So that is the integral. Then we know this should be evaluated from 0 to a, okay. And how does that work? We will substitute x equals 0, then write down the result, substitute substitute x equal to a, write down the result, substitute x equal to 0, and write down the result. We know that when we set in x equal to 0, this will give us 0, this will give us 0, so we can just ignore that. So by substituting x equal to a, we will have b into a to the power 3 over 3 plus b over a squared into a to the power 5 over 5. When we substitute 0 again, this will give us 0, 0, so we can just forget about that. So this is going to be b a cube over 3 plus, so this is a to the power 5 over a to the power 2. That's simply b a cube, okay, divided by, this is 5 divided by 5. And we can tidy this up. The LCM of these, we can say that is 15, and so this will be 5ba cube, and this will be plus 3ba cube. So with this, we have our results, and we can now tidy this up. This is going to be 8ba cube over 15. So therefore, our moment of inertia about the y-axis is 8ba cube over 15. So that is that about that for moments of inertia about the y-axis. So it is so interesting to deal with. Once you have the curve, you identify whatever curve you have there and its equation, get rid of whatever arbitrary constant or whatever constant is in the definition of the curve by just looking at one of the points that the curve passes through, which you know is coordinates. You can use that to evaluate the constant. Once you have the constant evaluated, then you can have your elementary strip analyzed. So what's important is you define your dA, that's the elemental area, by looking at the elementary strip. What will be the area of the elementary strip? So where you have that tiny width is the x. It's going to be the x. So if this were parallel to the horizontal, our tiny strip will just be, our tiny length will be the y, and we would have used that here. So this distance here is b minus y. So what's important is that whatever elementary area you're using, ensure that whatever definition of the area you've come up with applies, okay, to all cases where this thing has to sweep through the entire area. So if this thing is going to sweep through the entire area, it means that this elemental area, if I located it here, this definition will still apply. If I located it here, this definition will still apply. If I located it here, this definition will still apply. So if I located it anywhere on this, anywhere in this area, so far it is still vertical, this definition will still work for it. That is what is important. So um, once that is ascertained, then you are sure that then you can be sure that you have used a proper definition which will sweep through the entire area when it is integrated over the x. So we can see this integration over the x means that we are taking this small area and we are taking its moment about the second moment about the y-axis, and then we are integrating over the entire area. So it's like you are switching this over the entire area until the entire area is covered. So if your definition is not something that will apply for that horizontal or vertical strip that you have chosen, by sweeping it through the entire area, if it's not going to cover the entire area, it's not or it's going to cover more than by your definition by the time you position it at different points, then, or I mean by the time you imagine its position at different points, then you have not chosen an appropriate strip. Okay, so that is that about that. So what if you want to get moment of inertia about the x-axis? So if you want to get moment of inertia about the x-axis, how do we go about it? Of course, you might think of that and say, yes, I should solve this by using an elemental strip that is parallel to the x-axis, and you would be correct. That is correct. You can use an elemental strip that is parallel to the x-axis. So far you follow the definitions properly, you will still get a correct result. Okay, so you can do that. And if you were going to do that, you would have something like this. So if you want to get the moment of inertia about the x-axis, the same shape, we would have this axis. This is our x-axis. This is our y-axis. The same shape now. This goes up here, and this goes up here. We have this shape here, and I want to use a horizontal strip. So let's draw a horizontal strip. So here we'll have this as our horizontal strip. So in this case, we see that the tiny length here or width here is along the y-axis. So we can call this the y. And if we want to get the perpendicular distance from the x-axis, that's going to be given by this coordinate. So that is going to be our y, okay, for the elemental area. So if you want to get the elemental area, so let's think about what that would be. We're going to have our dA to be equal to, so the width of this is dy. So let's take note of that first, dy. Then what is our length? That is, what is this distance from this point to this point? So that's a problem. But we do know that the distance from this point, okay, to this point is b. Is that b or a? Go back to check the shape. We know that that distance is a. Is a, please? Let's correct that. So we know that this distance is a. So then we know at every point where if this strip is located here, then the value of this will be given by the x coordinate of this point. So this is just the x coordinate at this point. So if the strip was here, for instance, still horizontal, the value at this end will just be the x coordinate at this point. So if we want to get this length, it is going to be given by the x coordinates. You know, this length is what we need from the distance between this point and this point will be given by the x coordinates of this particular point. So basically, whatever the x coordinate is here is the same thing as the length of this elemental area. So this area will just be dy multiplied by x. That is the width of it, dy multiplied by this length, which is just x, the x coordinate of this point that we are, okay, wherever this elemental area is located. Okay, so with that, we are good to go. So we know this is y already. We can see it's already the perpendicular distance from the x-axis. We have our dA ready as well. So we can now say that I sub x is equal to integral of, that is y squared dA over the entire area. So how will this work now? This will be integral of y squared. Our dA is x dy, okay, over the entire area. So we have dy here. So how does the y coordinate, that's how does the y coordinate vary over the entire area? You know, by default it means that you have to sweep through. If you want to sweep through the entire area, you have to move um this rectangular strip or this horizontal strip. You have to start from here, place it here, place it here, place it here, place it here. You continue raising it up like that until you cover or sweep the entire area. So that is, we are going to be going from the lowest y coordinates, which is 0 at this point, to the highest y coordinates, which will be b at this point, because he already told us that the distance between this point and this point is b. So the highest y coordinate is b, the lowest y coordinate is 0. So we know the y coordinate at this point is b, so we can now tell ourselves that if we are integrating with respect to y and we want to sweep the entire area, then we must go from y equal to 0 to y equal to b at this point. So this is y equal to 0 to y equal to b. So we're good to go now. So the only thing still disturbing us here is x. We know x is not a constant, so we cannot possibly move it out of the integral sign. So we just have to find a way to relate it. So how does this x coordinate here relate with y? Because we want to integrate with respect to y. And that again takes us back to the equation of the curve. We have already obtained it here. So if we wanted to have x as a function of y here, we would have x to be equal to um, the square root. When we move this to the other side, we're going to have x squared to be equal to a squared, okay, a squared over b. Then multiply by y, this a squared over b multiplied by y. Then we, for us to get x, we take the square root of both sides. This will give us x is equal to the square root of a squared over b, okay, multiplied by y. So we have the root of y right here. So we can now use that expression here. So we know that this y coordinate is the y coordinate on this curve. And we know that this curve, how it relates to the y coordinate at any point is by that equation up there. So we can just bring that here now to simplify this. So this is going to give us the integral from 0 to b of y squared is not a problem. X, we now know that x is meant to be the root of a squared over b multiplying y. So this root covers everything. So root of a squared over b multiplying y. So that's it here. Root of a squared over b multiplying y. So with that, we will now just close this bracket. Then we're integrating this with respect to y. So this should be something easy to integrate because a squared over b, root of a squared over b, of course, that's a over root b is a constant, so we can move it out. So this is going to be a divided by root b. So this is a over root b. Then we have root y here. Root y is y to power 1 over 2. So what we have here will be y to power, what we have left after we have removed root of a squared over b, which is a over root b, will be y, that will be root of y, that's y to power 1 over 2, then multiply by y to power 2, that's y to power 2.5 if you like, or 5 over 2, that's y to power 2 plus 1 over 2. That should be 5 over 2. So this will be integral from 0 to b of y to power 5 over 2, then with respect to y. So with this, we can go ahead with the integration. So we integrate the same way. We can see that keeping out the constant still, we have a over root b. Then integral of this is going to be y to power 5 over 2 plus 1. 5 over 2 plus 1, what would that give us? Let's use our calculator. I can't wrap my head around that now. So this is going to be 5 over 2, then plus 1 plus 1. So that gives us 7 over 2. Okay. So then divided by 5 over 2 plus 1. So this is going to be 7 over 2 divided by 7 over 2. So let's explain this. Let's just cover that. And it will be evaluated from 0 to b. So we set y equal to b. We keep our result, then set y equal to 0 and keep the result as well. Subtract it from the previous one. So this is going to be a over root b into, so this is going to be b to power 7 over 2 divided by 7 over 2. Then minus 1, put 0 here, that's 0, so we can just ignore that completely. So what do we have now? We have this to be equal to a over root b, or b to the power 1 over 2, then multiply by b to the power 7 over 2, then multiply by, dividing by 2 over 7 over 2 is the same thing as multiplying by 2 over 7. So with this, we can simplify further. This is going to give us b to the power of 7 over 2. So if we subtract 1 over 2 from that, but I mean, when simplifying this power, this will be b to the power of 7 over 2 minus 1 over 2. So let's check that out. 7 over 2 minus 1 over 2 minus 1 over 2. That gives us 3. So this is going to give us 2 over 7 a b to power 3. So this is going to be our moment of inertia of the area about the x-axis. This gives us 2 over 7. And that is that about that. As expected, we should have dimension of length to power 4. Okay, so that's a confirmation, at least preliminary confirmation, or some level of confirmation at least. So there may be error here, but then if we get this, at least if we didn't get something that had dimension of L to power 4, we should be worried, and we should go back to check. But let's leave it at that. This is our results, of course, provided there are no errors here, but we can come back to verify that later. So we'll do that before we end this lesson. So these are our results for moment of inertia about y-axis. This is the result for moment of inertia about the x-axis as required in the problem statement. Okay. So now I want you to get something here, that this process of having to use a different elemental strip, yes, it's fine, it's correct, but it may not always be applicable. It may become difficult to actually use both a horizontal and vertical strip. So that is, you may have a figure that is more complicated, which for which you may not be able to easily get a horizontal and vertical strip at the same time. So if we didn't want to have this again, and we just wanted to just move on with the first strip that we had, then we can do that and still get our result. So how would we do that? So what we do is this. Now, of course, if we wanted to get IY, we would go about it the same way we have done. But if we wanted to use this same elemental strip to get our IX, that is moment of inertia about the x-axis, yes, we could, without going through all of the process of having to redraw with a different strip. So let's see how that works. Let's try to do that by this side. So what to do is this. We know this is a rectangle. I mean, it is being approximated as a rectangle. So we know already that for a rectangle, we can get its moment of inertia. So that means that instead of using the A, that is, instead of getting the area of this elemental area, why don't we just get the moment of inertia of this elemental area, then integrate over the entire area. So if we integrate over the entire area, we know it still gives us the same result. So instead of getting the A, why not get the IX? That is, get the moment of inertia of this elemental strip about the x-axis. And when we have that, why don't we just sweep over the entire area and see how that works out? So how do we go about that? We know that this is a rectangle, and for this rectangle, we can get the moment of inertia about its centroid. So if we locate the centroid of this rectangle, let's see how that works. We locate the centroid of this rectangle, we get the moment of inertia about the centroid of the rectangle, about an axis that is parallel to the x-axis, and through the centroid of the rectangle, then we proceed from there. So we will work with this elemental strip that we already formed. So we know that the moment of inertia, so let me just redraw that here so that we can easily refer to it. So we have this elemental strip already, x and y, and then we have this directed this way. We have a vertical strip. We know that this is approximated as a rectangle. So if we locate its own centroid, and we can get its moment of inertia about this. So say this is what do we call this now, y bar for this area, I mean this x bar for this, that's an axis. So let's say this axis is x bar for this elemental area. Then we can get the ix, that is the moment of inertia of this elemental area about this x-axis. What will it be? So the first thing we want to ask ourselves is, what will this distance be? Okay, so we're going to make use of the parallel axis theorem for this elemental area. So we know this is x bar. We know that this is our y. We know this length or this height is b minus y. Yes, that b minus y. Yes, we know this height is b minus y. So halfway between it, I mean this height is b minus y. So if we took halfway between it, that would be b minus y over 2. So basically, we know that from this point, okay, so this point will be b minus y over 2. So basically, this will be b minus y all over 2. And then this distance itself from this point to this point is going to be the distance here, which are the coordinates here, which is y. So basically this will be b minus y over 2 then plus y. That will give us this distance. You know, the distance we need is, if we want to use the parallel axis theorem, we need the distance from this centroidal axis to the parallel axis. So this is the parallel axis about which we are interested in the moment of inertia of this elemental area. So we're interested in this. This is our distance d that we're interested in. So from this, we can see that d will be equal to b minus y over 2 then plus y. So what does this give us? This is b over 2 minus y over 2 then plus y. That should be b over 2 plus y over 2. So this is going to be b plus y all over 2. So that is that about that. That is just the midpoint of the coordinates here, which is y, the coordinates here, which is b. So that's how we come about b plus y over 2. So anyhow you approach it is fine. So that is this distance from this point to this. So what will be the uh, what will be the, what do we call it now? The moment of inertia of this elemental area about the x-axis. So because it is moment of inertia of the elemental area, we call it the ix. So it is for the elemental area. We are going to integrate it so that we get ix. So what is the difference between this and what we have done before? We said we are still using the same strip that we used to get the vertical, the IY. We're still going to use it here. So this is the IX. It's going to be given by parallel axis theorem. It's going to be given by the IX bar plus the A. Okay, that's this area of the elemental area, and multiply by d squared. So our d is b plus y, okay, over 2. So we have b plus y over 2 all squared. So this, the ix, can help us obtain our results. Now, how do we get the ix bar? We know already that for a rectangular strip, The moment of inertia about an axis through the centroid of the area is given by bh cube over 12. We did that in the previous lesson. So for this one now, we know b, that's the length at the base parallel to the axis of interest, is this length here, which is equal to the x. So this basically is going to be equal to the x. So our b here is the x, our h will be the height in the other direction, which is b minus y that we've identified already. So basically, this is going to be this, the ix is going to be um, what do we call that now? We said it should be bh cube over 12. So b for this elemental strip is the x, this length here. So that's our b for this elemental strip. Yeah, this distance here is bx, and this vertical one here is our b minus y. Okay, so we're going to use that idea here. So for a rectangular strip, we know that it should be bh cube over 12. So b in this case is this base, which is the x. So this is meant to be the x. Okay, then h cube, that is this vertical height here, then raised to the power of 3. That other vertical height is b minus y. We've identified that before, so we can put this as, this is the x, then this is b h cube, which is b minus y, then to the power of 3, then divided by 12. Okay, then we add it to whatever we have here, plus the A. So what is the A? We already have that also from what we did here. Since we are using only this strip, we already have that. That is still B minus Y multiplied by dx. So this is going to still be B minus Y. So the A is B minus Y multiplied by dx. Okay, multiplied by dx. Then multiply by this B plus Y, okay, all over 2 all squared. So this is B plus Y over 2, that's over 4. When we square this is 4, and this is b plus y all squared. So this will give us our the ix. We can tidy it up even further. We're going to have this to be b minus y to the power of 3, okay, divided by 12. So this is going to be divided by 12, then multiply by the x, then plus this, we have b minus y multiplied by this b plus y all squared. So this is going to be equal to b minus y multiplying that, then we can put in the x separately. So this is going to be b minus y, sorry, we don't have this code here. So this is going to be b minus y multiplying b plus y all squared, all divided by 4, then multiply by the x. So that is that about that. So we have our expression for the yx, sorry, the ix. So if we want to get ix, we can then integrate this. So when we integrate this, it will give us ix. So if we're going to integrate this, we will be integrating with respect to x. Of course, we should not forget the definition of our y. Our y is b over a squared multiplied by x squared. So we will definitely have to put that here when we will have expanded whatever needs expansion here. So um, that is another way. That is the way that we can get the what do we call it now? The moment of inertia of this area about the x-axis without using a different elemental strip. So this is clearly more involved. It will take a lot more work to do because this shape is not in simple form, in that we will have to first translate whatever the moment of inertia is about this axis. We will have to first translate it to this base. So if it was a case where we add it to the base already, it will be easy for us to translate it to the other axis. So for this case, it is not profitable because this is obviously more complicated. But of course, we can go through it, substitute for y here with this expression, which is y equals a squared over b, y squared equals b over a squared x squared, and then do this integration. This integration is with respect to x, and you have it over the entire area. When you do that, you get your result, and that will be totally okay. All right, so it will not be a good process to go through because that will take a long time. Now that is that for if you wanted to use that same horizontal or vertical strip to get the moments of inertia about the x-axis. So let us have a look at this second one. Now we have this, we have used it for moments of inertia about the x-axis. We have our results. Now what if we wanted to use this same thing for moments of inertia about the y-axis? Now you see the difference. Now this is the elemental area. What is the moment of inertia of this elemental area about the y-axis? That is straightforward because y is at the base of this elemental area. And we know the moment of inertia about the base directly. We don't have to get it about the centroid and then translate it to the base. So in this case, will be the ideal choice so that with this singular strip, we are able to get moment of inertia about the x-axis and also get moment of inertia about the y-axis quite easily. So let's see how this will work out. So if we consider, so we are done for this part, we've done the moment of inertia about the y-axis. Now if we consider this elemental area, what will be its moment of inertia about the y-axis? So that's what we call the IY. Why are we using the? Because it is for the differential area or elemental area. So we know this thing here is this axis, this y-axis is at the base of this elemental area, and we can recall that for a triangle of for a rectangle, when we have it at the base of this or the base of y here or the base of x here, and we have this to be b and this to be h, we have said that moment of inertia, we've obtained this result before, and I said you should memorize that about the y-axis will be h b to power 3 all over 3. If it was about the centroid, we saw it would be over 12. So in this case now, taking this as our area, this elemental area is now our area. What will be the base, the height at the base? The height, I mean the width of at this base here, the width at this base. You know, here we took the width at the base of the axis of interest. This is the axis of interest. So its width along that direction is h. That was the one that was not raised to the power of 3. So if we take this one now, this rectangle, this small rectangle, the distance here along the y-axis is what we have denoted as dy. So this will definitely be dy multiplied by b. Our b is the distance along the perpendicular direction. That is this distance. And we have seen already from what we have done that that is just x. This distance will be given by the x coordinate of wherever the strip is. This will be multiplied by x, then to the power of 3. Then what else do we have? All over 3. So this everything here divided by 3. That gives us the moment of inertia of this elemental area about the y-axis. So if we are going to get the moment of inertia of the total area, then we just need to integrate this. So going with this integral, we already see that dy is here. So this integral has to be evaluated along the y-axis. So if that is the case, we should replace this x here. And of course, we already know our x is equal to root of a squared over by. So we can just insert that here. So from this, we see that our diy will be equal to x to power 3. Our x to power 3 is root of a squared, that is a over root b. Okay, we wrote that as a over root b the other time. Yeah, a over root b multiplying root y. Okay, all raised to power 3. That's x. We have replaced x by this expression. We know that on the curve x is equal to this, so that's what we've done here. This is root of a squared is a, so then root of b, so a over root of b, then root of y, then everything raised to the power of 3, then divided by 3. Then we have dy, so this is going to be dy. So iy will be integral of this, integral of this, of course, over the entire area. So we're integrating with respect to y. Again, we know that over the entire area, y varies from 0 to b as we have obtained it here. So this will still be from 0 to b. So we now find out what this will give us when we integrate completely. So it will give us our moment of inertia about the y-axis for the entire area. So this is going to give us iy, integral of 1 diy, that is just iy, and this will be equal to, so let's see what this gives us. A over root b is a constant, so we are raising it to the power of 3. That is going to be a to the power 3 all over b to the power 3 over 2. Okay, because of root b that we have there and raised to the power of 3. And then we're going to have this to be everything here is still divided by 3 because of the 3 here. We moved it out as well. Then what we have left to be integral of this is y to the power 1 over 2, then raised to the power 3. That is y to the power of 3 over 2. Then we do this with respect to y. So let's see what this gives us from here. This will be equal to a to the power of 3 divided by 3b to the power of 3 over 2. Of course, this is still evaluated from 0 to b. So if we integrate this is going to be y to the power of 3 over 2 plus 1, that is 5 over 2, divided by 5 over 2. And we will take this or evaluate this from 0 to b. So if we set y equal to b, we get b to the power of 5 over 2. If we get y, if we equate y to 0, that will be 0, so we won't have to bother about that. So to move forward with this, we will have our moment of inertia about the y-axis to be equal to a to the power of 3 divided by 3 multiplied by b to the power of 3 over 2, then multiplied by, when we substitute b here, this will be b to the power of 5 over 2, then divided by 5 over 2, that's multiplied by 2 over 5. And what does this give us now? We have the other part here to be 0. So from here, what do we get? This is going to be b to the power of 5 over 2 minus b to the power of 3 over 2. So b to the power of 5 over 2, that is going to be 5 over 2, 5 over 2 minus 3 over 2. So that is 1. So this is going to be b. This will be b b a to power 3 divided by, what do we have here? This is 3 multiplied by 5, that is 15, and then we have this to be 2. Okay, so that is what we get using this approach. Is it the same as what we have up here? Let's check if there is any issue with what we've done here. So we have just obtained 2b a cube over 15, okay, which is fine, which is it the same as what we have up here? No, it's not the same. We have 8b a cube over 15. So let's check. I think there could be an error here. Oh, this is meant to be negative. This is meant to be negative. Sorry. This is minus here, and this is meant to be minus. So this is minus, this is minus, this is minus, and this is minus. So this is meant to be 5b a cube minus 3b a cube, which is 2b a cube over 15. So that is that about that. That is the moment of inertia about the x-axis. And so that's the process for getting the moment of inertia by direct integration. So again, to repeat, when it is feasible, the simplest way to get a moment of inertia is to, for each of the axes, form or use a rectangular strip that is parallel to that axis. So if you want to get a moment of inertia about the y-axis, use a rectangular strip that is parallel to the y-axis. If you want to get a moment of inertia about the x-axis, use a rectangular strip that is parallel to the x-axis. That gives the simplest way to actually find the moment of inertia by direct integration. But where this is not feasible, maybe it's going to take a lot of time or it is not so straightforward to obtain, then once you have one of them, you can use it to get the other. Okay, and you just have to look at what process is involved and see if it is something you can go through and make it easy to obtain. Then you are good to go. You can do that. Okay, so for this case, we have used the rectangular strip which is parallel to the x-axis to get both the moment of inertia about the x-axis and moment of inertia about the y-axis, and of course it served as confirmation for us that this is the result. This is meant to be 2ba cube over 15, and this one is 2ab cube over 7. So that is that about that. We will see in another lesson when we consider some other examples about composite areas that we could have more simply actually obtained the moment of inertia also about the x-axis by writing out the expression for this moment of inertia of the elemental area in a simpler way, okay, other than using the parallel axis theorem by taking summation I mean subtraction of moments of inertia. So we'll talk about that when we talk about um, composite areas, how to get moment of inertia of composite areas. Thank you for watching. We'll proceed in the next.